You have hit the ceiling on vertical scaling. You have bought the biggest machine your cloud provider sells and the app is still struggling under load. You cannot make the box any bigger. So what do? You stop trying to make one box bigger and you start running more boxes. That's horizontal scaling. And on paper it sounds obvious. Just add more servers. But the moment you do it, you discover something nobody warned you about. Adding more server does not just solve the load problem, it creates a whole new category of problems. Problems about traffic, about state, about shared data. In this video, we will cover what horizontal scaling is and how it works, and most importantly, exactly which new problem it introduces, because the rest of this module exists to solve those problems one by one. Let's get into it. Horizontal scaling means adding more machines to your system instead of making one machine bigger. You take your application and you run multiple copies of it, each on its own server. Traffic gets split between them. Each server handles a portion of the total load. If vertical scaling makes the box taller, horizontal scaling makes the boxes multiply outward. That is why it is called as horizontal. You are expanding sideways, not upward. The key difference is that with vertical scaling, you are always working with a single machine. With horizontal scaling, you have a fleet, 2 servers, 10 servers, 100 servers, all running the same code, all handling requests in parallel. This removes the ceiling entirely. When you need more capacity, you spin up another server. When load drops, you shut one down. On modern cloud infrastructure, this can happen automatically, a practice called auto-scaling. Stick this in your brain forever. Horizontal scaling means more copies of your application running in parallel, not a bigger version of the same machine. The ceiling disappears, but the complexity multiplies. Think about a post office. In a small town, there is one post office branch, one counter, one team of staff. It handles everything: sorting the mail, receiving parcel, answering customer questions at low volume. It works fine. Then the town grows. More people, more mail. The queue at the single post office stretches out the door. The staff is overwhelmed, so the town opens more branches across different neighborhoods. Now traffic is distributed. Customers go to their nearest branch. No single location is drowning. That is horizontal scaling. But notice what just got complicated. When a customer wants to pick up a parcel they dropped off at the north branch, they cannot just walk into the south branch and expect it to be there. The parcel is on a specific shelf at a specific location. If the branch do not coordinate their inventory, customers get the wrong answer at the wrong counter. What does the town have to do? It needs a central directory system that all branches share. It needs a rule about which branch a customer should go to, or a receptionist at the entrance who directs them. And it needs a way to keep all branches updated with the same information. In your distributed system, that central inventory is your shared database. The receptionist is your load balancer, and keeping the branches in sync is the session and a state problem. One branch was simple. 10 branches solves the capacity problem and create a coordination problem. That trade-off is the whole story of horizontal scaling. There are 3 reasons horizontal scaling is a backbone of every large system you have ever used. Reason 1. It is the only way to truly remove the ceiling. Vertical scaling eventually runs out of road. Horizontal scaling does not. Every major platform, social media, streaming services, payment processor runs on horizontal scaling because the traffic volume would overwhelm any single machine. Reason 2. It gives you redundancy. With multiple servers running your application, one going down does not mean the whole system goes down. The load balancer in front of your fleet stops sending traffic to the failed server and routes everything to the remaining one. This is how system achieves high availability. Reason 3. Everything that comes after in this module is built on the top of horizontal scaling. Load balancers, caching strategies, database replication, message queues, all of these concepts assume that your application is already running on multiple machines. Without understanding horizontal scaling, none of the rest of the course makes full sense. Here's where we are going. Let's walk through the architecture. The left side is your users, browser, mobile app making requests. Every request comes in from the internet. Those requests do not go directly to your servers. They go to the load balancer first. The load balancer is the traffic director. It sits in front of your entire fleet and decides which server should handle each incoming request. Round robin, list connection, random. There are different strategies and we will cover them in the next video. Behind the load balancer are your application servers, 2, 3, 10, it doesn't matter. They all run the exact same code. Any one of them can handle any request. The load balancer keeps the work evenly distributed across all of them. On the right side is your shared data layer. This is the critical part. If every server has its own private database, they will give different answers to the same question. You need one shared database that all application servers read from and write to. You also typically have a shared cache. Redis is the most common choice, so all servers can share fast access data without each one going directly to the database. Now, horizontal scaling creates three problems that every production system has to solve. Problem 1. Traffic routing. Without something in front of your server, requests have no way to find the right destination. This is the load balancer's job. We cover it in the next video. Problem 2. Session state. Imagine a user logs in on server 1. Their session is stored locally on server 1. Their next request lands on server 2. Server 2 has never seen this user. They appear logged out. This is the session state problem, and it is solved by storing session in a shared store like Redis that every server can read. Problem 3. Database pressure. 10 application servers all writing to a single database is 10 times the write pressure on one machine. Eventually, that database becomes the bottleneck. This is solved through database replication, read replicas, and eventually sharding concepts we built up to later in this module. Every one of these problems has a dedicated solution in this course. That is what the rest of the module 4 is about. I want to be honest with you about something most courses won't tell you. The good news is horizontal scaling removes the ceiling. It adds redundancy. It lets you scale individual part of your system independently. If only your application tier is overloaded, you add more app server without touching the database, and cloud platforms make it relatively easy to spin up new instances automatically when load spikes. That is real. The bad news, your application code has to be designed for it. If your app store any user state locally on server, in memory, on local disk, horizontal scaling will break it. You need stateless application server. Everything that needs to be persist between the requests has to live in the shared data layer. This is not a small change for existing system, and teams often underestimate it. When not to use it? When your application is not at stateless and you do not have a bandwidth to refactor it. In that case, push vertical scaling further while you prepare for the transition. By this time now, you have acquired knowledge to answer this interview question. Question 1. What is horizontal scaling and how is it different from vertical scaling? Horizontal scaling means running more copies of your application on separate machines and distributing traffic between them. Vertical scaling means making one machine more powerful. Horizontal scaling removes the ceiling and adds redundancy, but it requires your application to be stateless and introduces new coordination problem around traffic routing and shared data. Question 2. What does it mean for application to be stateless? Why does horizontal scaling require it? A stateless application does not store any user-specific data in the server's local memory between requests. Every request contains all the information the server needs to respond, and the server does not remember anything after the response is sent. Horizontal scaling requires this because requests from the same user may land on a different servers each time. If one server holds user state that another server cannot see, your system breaks. Question 3. What new problem does horizontal scaling introduce? Three main ones. First, you need a load balancer to direct the traffic. Second, session state cannot live on individual server. It needs a shared store. Third, a single database can become a bottleneck when many servers write to it simultaneously. Each of these has a solution, and knowing all three shows you understand the whole picture. That third question separates candidates who have read about scaling from candidates who have actually thought it through. Before you go, take 30 seconds to log this in. Takeaway 1. Horizontal scaling means running multiple copies of your application on separate machine. More boxes, not a bigger box, with a load balancer distributing the traffic. Takeaway 2. It removes the ceiling and add redundancy, but it requires your application to be stateless. Any server local state breaks the model. Takeaway 3. It introduces 3 new problems: traffic routing, session state, and database pressure. The rest of the module 4 is essentially a course on solving those 3 problems. Horizontal scaling is not the end of the story, it is the start of the real story. In the next video, we are digging into load balancer, what they are, how they route traffic, and the strategies they use. Hit subscribe so you don't miss the next one. The full playlist is in the link below. See you in the next video.